Today's video is going to talk about transformations of exponential functions. So when we talked about the original parent function of an exponential function, it was b to the x power. So that's this section of this big long equation. Everything outside of that b to the x power is a transformation of that parent function. So a will make it move certain ways, h will make it move certain ways, and k will also make it move certain ways. But b to the x is the original generic shape that we've already talked about that has, consistent characteristics like consistent domain and range and in behavior and all that. Today, we're going to learn about things that change all of those characteristics. So h, in the exponent with the x, h is the horizontal shift. And I just think h stands for horizontal. But I want you to notice that it has a negative there. So I want you to consider this opposite h. So I want you to think of it as opposite h, because if h is positive, so if that was an x plus 2, that would shift left. And then if your exponent was x minus 2, that's going to shift to the right. And that's kind of the opposite of what you would normally think because, positive numbers are on the right side, negative are on the left. So you just need to remember that h moves in the opposite direction of what you would normally think. K on the end of it is the vertical shift. And this one is normal. Positive shifts up and negative will shift down. Then we're going to look at A. And A is in the rest of these three bullets. So there's a lot to pay attention to with A. If A is negative, then the function is reflected across the x-axis. If it's positive, then you don't have to consider anything because the parent function technically has a positive 1 as its A value. So you really don't have to, it doesn't change from the parent function unless it's negative. But then once you look at whether or not it's negative, we have to look at the actual number and see, is that number without its sign, is it greater than 1 or is it between 0 and 1? So if it is greater than 1, that is a vertical stretch. So for example, if it was a 2, in my mind, it increases twice as fast, so it stretches up faster. And then if it's between 0 and 1, so like 1/2 or 2/3, that represents a vertical compression. So it increases half as fast or 2/3 as fast. Okay, so it is a little bit slower increase. So for number 2, as an example, we are going to talk about the transformations. The first thing it tells you to do is to identify the parent function. And I'll just have you do this by drawing a rectangle around the b to the x portion of the function. So 1/4 to the x power, that is our parent function. So it's always going to be the x and whatever is attached to it as its exponent or as its base. So everything that is not in that box I just drew has to have an explanation. So we're going to start left to right. We're going to start with this 2. And 2 is in the place of a. And if you look back at your bullet points at the top of your worksheet, it says if A is negative. This is not negative, so we can skip that bullet point. But then we have to look, is 2 greater than 1 or is it between 0 and 1? It is in fact greater than 1. So this 2 makes our graph have a vertical stretch. So we're going to say vertical stretch, and you can abbreviate this by 2. And you have to include the numbers in there. Vertical stretch is not enough. We need to know by how much. So we have explained away that 2. Now we need to look at this -1 up here. That is in the place of h. So we're looking at our bullet points at the top. We're looking at the h one. That's the horizontal shift. And it is going to shift right because it's a -1. So we are just going to put right 1. So we took care of the 1 now, and that's it. We're done. So our parent function stretched by 2 and moved right 1. All right, number 4, another example of this. 5 to the x power is our parent function. Everything else has to have an explanation. So first, let's look at the 1/2. That's in the spot of a. First, we have to look at the if a is negative bullet point. This one is not negative, so again, we can skip that. Then we look at, is a greater than 1 or between 0 and 1? And it's between 0 and 1. So this has a vertical compression by 1/2. And that takes care of A. Now we're looking at H, -4. That's going to shift right 4. Then we're looking at K. It is also going to shift down 2. And that's all we have to do for this one. All right, so for number 5, we're going to start graphing and talking about the characteristics. So first, let's take a look at this on our calculator. All right, so we're going to go to y equals, and we are going to type in our function. 2 to the x plus 5 power, and hit graph. Okay, so our function has moved from its original position as a parent function. It's moved to the left. So if we go to our table now, I had mentioned that we would normally graph from like -2 to +2. But if you look here, if we start at -2, we get to plot the point 8, and then that's the only point we would get to plot. So what you're really looking for is points that fit on your graph. So the first one at the bottom end is at -2, 8. And we can fit all of these on our graph until they start getting too tiny. So I'm going to go from -7 to -2. And those are the points I'm going to graph because that's what actually fits on my graph. Okay, so on my graph, my points were -7 up 1/4, left 7 up 1/4. Sorry, my pen's not working. There we go. And then left 6 up 1/2, left 5 up 1, left 4 up 2, left 3 up 4, and then left 2 up 8. And that's all that will fit on my graph. So now I can make my line, my curve, and go from there. All right, so my domain is still going to be all real numbers. For every exponential function that we graph, the domain will be all real numbers. Our range, in this case, our graph did not move vertically in any way. This is why it's important to know transformations. If we look at this, we should see that the only transformation we have from the original parent function is that it's going to go left 5. So since the range is our y values, which are vertical, these haven't changed. Our function moved left. It did not move up or down. So our range, just like in our parent function, is going to be y is greater than 0. On the left side of our graph, our y value approaches, on the right side of our graph, our y value approaches positive infinity. On the left side, it approaches 0. Our y-intercept here is not on the graph, actually. We're going to have to go back to our calculator to find this. So on your calculator, if you look at where x equals 0, it tells you that the y value there is 32. You could also do it mathematically by plugging 0 in for x. That would equal 2 to the 5th power, which is 32. And so you would still get that same point. Then our asymptote, as always, corresponds with our range, y equals 0. Now we're going to look at a function that does move vertically, and we're going to see how that affects all of our characteristics. So we have 1/3 to the x power and then -2. So we should recognize that as, first of all, it's going to be an exponential decay because the b value is 1/3. And then our function is also going to go down 2 units. So there's no horizontal shift here, but it will go down. And I want you to go to your table on your graph. So put this in your y equals, go to the table, and we're going to graph all the points that fit on our graph. And in this case, it's really not very many of them. So we can start at -2, +7. There's a point there. -1, +1, we have a point. 0, -1, and then 1, and then down 1.6. So over 1, down 1.6 is somewhere here. And then it's going to get really, really close to -2, but it's never going to touch -2. Because normally our asymptote is at y equals 0. But we shifted our graph down 2. So it makes sense that now instead of never touching 0, it never touches -2. So let's go through our characteristics. Our domain, again, is always all real numbers. Our range this time, normally it is y is greater than 0. This time we shifted down 2 units, so y will be greater than -2. On the right side of our graph, our y value approaches -2. On our left side, our arrow points up to positive infinity. Our y-intercept is at 0, -1. That one's actually on our graph this time. And our asymptote, as always, coincides with our range and is at y equals -2. All right, thank you guys so much for watching, and you have a great day.